Hello, thank you very much for coming. Here we are presenting script gadgets, as he explained. I'm presenting together with Koto and Sebastian. And yeah, so what we want to show you today is how we bypassed every XSS mitigation we tested, which essentially means we tested XSS filters, web application firewalls, and several versions of content security policy, as well as a couple sanitizers. And the objective of this research originally was just to bypass CSP, but then it evolved into something a bit more generic. And we hope you like it. The website will post a copy of the repository, but there's another version online if you want to see the proof of concepts. So a quick agenda of what we're going to do. So I'm going to give you a very quick introduction for around 10 minutes. Then Koto is going to present the gadgets in libraries, which is the research done manually by us. Against the most popular libraries we came up with. And then Sebastian will talk about gadgets in websites. So we run a study around Alexa Top 5000 and then try to find gadgets automatically and generate exploits automatically. And at the end, we're going to just have a very brief summary and conclusions. All right. So most of you, I hope, are familiar with the term XSS, but I'm going to just give you a 30-second summary. So what you do in XSS is you have something like that. And the attacker does something interesting. If you're just pen testing, you just alert one or alert something else. So the right way to fix XSS is to do the right type of escaping in the right context. So in the previous example, it will be HTML entities, but it depends on what type of vulnerability you have. And doing this by humans is very difficult, so the right way to do it is to have your templating system do it for you. And this has proven to be very difficult for the industry, and in our case, we work in Google, and we also had troubles. This is a graph representing the amount of money we've paid as part of the Google Vulnerability Reward Program, and it represents how much we paid for XSS and for everything else combined. And as you can see, the vast majority of bugs is XSS, like 2/3 or so. So fixing XSS is hard, or at least has been hard for us. So let's instead focus on mitigating the attack. So what that means is that there are mitigations, and that's what we're going to talk about in this presentation. That rather than fixing the bug, try to mitigate it, or try to make the attack harder or impossible in some cases. This is very common for binary bugs, where you have ASLR and DEP, and etc. And for the web, we have other mitigations like CSP, XSS filters, WAFs, etc. So one important thing that we want to make sure it's clear is that these mitigations do not fix the bug. They leave the lack of escaping there, but they make the attack either impossible or really, really difficult. Or that's what they attempt. So in the context of this presentation, we're not going to teach you how to find XSS. We assume that they are everywhere and easy to find, as we have, seen in our past decade or so. So we want to bypass the mitigations that make the exploitation of those bugs harder. So during this presentation, you should assume that you have an XSS and you are stopped by the XSS filter or by something else in the middle, and you want to bypass it to show a better POC or to, steal some cookies or something. So all these mitigations work very similarly. They all look at dangerous tag or attributes, like WAFs and XSS filters block the request, HTML sanitizers clean them up from HTML, and CSP, before they get executed, they look if it's something that is trusted in some way, like whether they have a hash that is trusted or comes from a legitimate place, or they have a secret nonce, or they were injected dynamically correctly, etc. And so this is an example of, just to give you a brief introduction about how they are different and how they are the same. So this is a website. You go to the Happy Cloud responds with an XSS. So if you have mod security or web application firewall, then it stops it at the request level in the cloud. Then if you have no script in Firefox, then what happens is that it gets blocked before the request is made. So no script detects that this looks like an XSS, and then it stops it. Then Chrome and Internet Explorer work differently. They see the request and they see the response, and then they block the attack if the response is in the request, and it looks like an attack. And finally, CSP ignores the request at all, and then just sees, like, is this XSS, is this payload good or not? And if it's not, then it blocks it. All right. So with that introduction to mitigations and what is XSS, then we are going to talk to you about what is script gadgets. So we're going to give you a very simple example of what is the simplest, most obvious, the lamest script gadget that we have, right? So we have a script gadget in this case will be the following. So you have HTML snippet that doesn't do anything. It just has a div that has a couple attributes and has I am a button. And then there is some script somewhere in the page that activates that HTML and does something else with it. Maybe it wants to have some pretty CSS or something like that, and it just adds it somewhere else. So in this case, then it takes the HTML of that attribute and it detects the content of that attribute and puts it as HTML. So in this case, then if you have a mitigation, this is what will happen. So you have, instead of injecting that, you inject a div that just has a script tag in the data attribute. And the sanitizer will just allow it because, of course, like there's nothing wrong with that. But because there is a snippet of code that activates it and that executes it. And then you just have a normal, traditional script XSS. So just to summarize very quickly, what happens is that they convert the otherwise safe attribute into something active. And instead of injecting a script, which will be detected by all these mitigations, then you just inject something else. And these bypass XSS that look for this. And then what we want to do now is to try to figure out how prevalent these snippets of code are. Like maybe they never happen, maybe they happen sometimes. So as a preview of what we're going to present later today, or later right now, gadgets are present in all but one of the tested popular web frameworks. So you use one of the popular web frameworks. They are in all of them except React. Gadgets can be used to bypass most mitigations. So we bypassed all the mitigations in several. Some mitigations are bypassable in some frameworks, some aren't. So all of the mitigations were bypassed. All of the frameworks except one was bypassed. And we also created exploits for websites on the internet. So for code that is not in frameworks or libraries, but custom made, we were able to automatically find and generate an exploit for 20% of websites in Alexa Top 5000. There is a lower bound. We think that the actual number is way higher. Okay, so with that, Koto is now going to talk to you about the userland study, not the other one study.
Thank you, Eduardo. So, script gadgets in JS libraries. You already know what script gadgets are. Those existing snippets of code in the website that sort of upgrades the HTML that's present and looks benign to XSS mitigations into something that will execute code, right? And when we encountered this problem, we started thinking, is this thing prevalent? Like, are gadgets common? Are those snippets existing in most of the websites, most of the frameworks, or is it something really exotic that's not really, with no practical use for the attackers? And second of all, given that we find a couple of gadgets, or lots of them, how effective they are in actually bypassing the XSS mitigations? Because that differs for every class of mitigation. So we started from those two questions, and first we started looking at JavaScript libraries and started looking for gadgets in this code base. So we took 16 popular web frameworks or JavaScript libraries. We included AngularJS, we included Polymer, included React, jQuery, Knockout, Backbone. All that we considered popular and modern was on that list. Then we started just simply manually looking at the code of those libraries in order to find script gadgets. So for every library in this list, we were trying to bypass every of the mitigations tested. So we took a couple of XSS filters, we took a couple of sanitizers, we took only one example of web application firewall, the OWASP mod security with the core rule set, and we took several variants of content security policy. So we had like a matrix of libraries and mitigations, and we tried to come up with a bypass example for each cell in this matrix. So in order to describe this, it's best to start by looking at the gadgets by the mitigations they target. So first, let's talk about web application firewalls and the XSS filters. They detect XSS attempts by looking at the request parameters, sometimes using regular expressions, sometimes using a more elaborate logic, but essentially that's what they target, the request parameters. And we thought initially that gadgets, if they existed and if they were prevalent, they would be really successful in bypassing this kind of XSS mitigation solely because how gadgets work. Most of them, they allow for encoding the payload in a different context. You will see an example later on. Some gadgets also pass the code to eval, and usually we don't have to include the eval function in the payload, in the HTML snippet that we try to inject into the website. So this would be detected by web application firewalls pretty easily. But since we do not need to inject the eval, the literal eval function, then it would allow us to bypass those mitigations. It would be transparent to the mitigation. And finally, most of the gadgets do not require us to inject any script tags, any on inline event handlers, so something that is very obvious as an XSS attack attempt. So let's look at an example. There's a knockout JavaScript library, and this one has like a small templating language inside of it. So this HTML snippet actually tells the knockout to look for, to inject hello world as a string into the content of this div element, right? Using some custom language for knockout in specific. What this snippet triggers in knockout is several gadgets. First gadget is a fairly simple one. It just gets the content of the data bind attribute and assigns it to some variable in the application. Later on, knockout creates a function, a JavaScript function. In the body of that function, there is the hello world expression. So literally, there is a new function created by knockout that will contain something originally present in the HTML code that we, I assume, injected through some injection flow. And finally, the last gadget that we need to complete the chain is knockout will execute that newly created function. So that's all we need to actually construct an attack that would bypass the XSS filters and web application firewalls. So to summarize, there is a gadget in knockout that upgrades the value of the data bind attribute into an eval call. The function constructor is essentially an eval equivalent in JavaScript. So in order to XSS a website that happens to use the knockout library, and also on top of that uses an XSS filter on a web application firewall, instead of injecting script or, I don't know, image source equals X, on error equals your payload, it's enough if you just injected this fairly innocent looking to the mitigations div element. But there are way more examples of that. So in Bootstrap, you can have tooltips. Bootstrap is a UI component library, and most of the components can also be accompanied by a tooltip. So if you mouse over a certain element, there would be some new content displayed. Fortunately for us, this content can also be HTML, but it's being taken from the title attribute. So we can just encode it correctly according to, say, HTML specification, correctly in the attribute value context. And this script payload is completely transparent to the XSS mitigations, and we are able through that we are able to leverage Bootstrap into activating our payload for us. Or a similar example in Dojo Toolkit. It's also some kind of UI component library. So what Dojo does, it just takes the value of the data Dojo props attribute, concatenates it with some strings, and then passes it to the eval function, which is everything that we need in order to bypass the web application firewalls and XSS filters, because for the XSS filter, I don't actually see the JavaScript code, right? If I would be an XSS filter. Thankfully, I'm not. Okay, to briefly summarize this section is what we found out is most of the frameworks actually contain gadgets like that are successful in bypassing web application firewalls as exemplified by the mod security core rule set and the XSS filters built into the browsers. So, for example, we were able to bypass Chrome XSS Auditor in 13 out of 16 libraries that we tested. Mod security we were able to bypass in 9 libraries, and so on and so forth. Let's go to the next section, HTML sanitizers. Sometimes web applications actually need to display untrusted HTML content coming from the user. Like, let's say you have a webmail application. That's a very common example. So that's where HTML sanitizers come into place. They take this untrusted content, try to filter out everything that's bad, that would contain JavaScript, and leave everything else intact. So, for example, script elements would be removed, on error and other inline event handlers would be removed, but, I don't know, a p tag would be left intact. Some sanitizers often whitelist the data attributes. This is a recently new addition to the HTML specification that usually contains, well, data, right? So that's not code, it shouldn't actually be removed. Gadgets, we found, are really useful in bypassing HTML sanitizers for two reasons. First of all, this JavaScript code that we want to execute can be present in those benign attributes, like ID or title or other attributes, as you will see soon. And the second reason is that the gadgets very often leverage the data attribute values. So you actually put the parts of the payload or parts of the code into data attributes. And the frameworks themselves do the heavy lifting into upgrading it and actually executing that payload, transparent to the HTML sanitizers. So a couple of examples. Ajaxify, for some really weird reason, decides that a div with a class of document script should actually be created as a script, and the text content of this element will be the body of the newly created and inserted script. But that's common, like such patterns are very common. And this is why actually gadgets are interesting as an XSS bypass mechanism. And the same example as before, right? Bootstrap. It turns out that the very same vector also works brilliantly for bypassing HTML sanitizers, which exemplifies the fact that you don't need to find a unique gadget for every XSS mitigation. Sometimes a single gadget can bypass a couple of them unmodified. To briefly summarize this, we were moderately successful in bypassing the HTML sanitizers with the gadgets that we found in JS libraries. So yes, for DOM Purify, we were able to bypass the HTML sanitizers in 9 JavaScript libraries out of 16. In Clojure HTML sanitizer, it was only 6 of the libraries. And finally, let's get back to the finest of the XSS mitigations, maybe, or at least the most, I don't know, sexy one. Content security policies. Content security policy works on a completely different level. It doesn't try to identify anything in the request parameters. It only tries to distinguish trusted scripts from untrusted scripts using various means. And of course, untrusted scripts are being stopped from executing. So depending on the CSP mode, the way that a policy determines which scripts are trusted, so coming from the application author and not the attacker, there are different ways of determining that. So first one, the most popular traditional one, I think it was the first mode of CSP actually, is the whitelist, right? So you have a whitelist of URLs or whitelist of origins, and only scripts loaded from those origins are allowed to execute. Then there's a second mode of operation of content security policy, which is nonce-based. So trusted scripts are recognized by having a correct nonce secret value that is unknown to the attacker. So if an attacker injects a script that doesn't carry the correct nonce value, it would be stopped from executing. Unfortunately, it turned out that content security policy is pretty hard to adopt on existing websites. So the community came up with a list of CSP keywords that make the adoption a little bit easier at the expense of the security. So let's first start looking at those additional keywords. First one is the unsafe eval keyword. And what it adds to the policy is a slight relaxation. So your trusted scripts are now allowed to call an eval function, which seems simply benign. I mean, you shouldn't pass anything untrusted, and the scripts were loaded from, say, a good origin, so what's the worst that can happen? Well, gadgets are the worst that could happen, maybe. It's pretty obvious how we can use gadgets to bypass the unsafe eval version of content security policy, simply because a lot of gadgets, well, call eval on something coming from the HTML that can be injected by the attacker. As an example, underscore library is a templating library as well. So we can simply inject an underscore template that contains this special syntax for underscore, the percent tags, and whatever is inside those percent tags will actually be passed to eval. So that's a very simple example. Then came strict dynamic, a recent addition to content security policy. Strict dynamic is the relaxation that allows the trusted scripts to programmatically, dynamically create new script elements. And those new script elements would be blessed by the content security policy. So they would not need to have a correct nonce value, for example. They would be trusted solely because they were created from a trusted root, let's say, right? So an already trusted script. It turned out that gadgets are quite successful in bypassing content security policy with strict dynamic. Solely because creating new script elements from something that was already existing in the DOM, in the HTML code of the web page, is a common pattern in those libraries. As an example, let's look at the jQuery mobile. So what we have here is some pop-up functionality of jQuery mobile that allows this library to enrich a certain HTML element with additional behavior. But as a hint to debugging the applications, jQuery Mobile will insert an HTML comment with the ID of the attribute that was just enriched. Unfortunately, they do it in a pretty unsafe way. So we can simply escape the comment, as you can see in the ID attribute, and start injecting our HTML code. Which is, by the way, we could HTML escape the script tag here. It wouldn't matter, right? So there would not be a literal script tag there with the angle brackets. So when jQuery Mobile inserts this ID attribute into the web page, it defers to the jQuery HTML function. And jQuery HTML function is a wrapper over inner HTML assignment with one exception. And that exception is that it tries to look for script tags in the string and creates them dynamically instead of just passing them to inner HTML, because adding a script element through inner HTML would not work for various reasons. So jQuery has a workaround for the behavior, and that particular workaround allows us to use jQuery as a gadget in jQuery Mobile in this particular example. So if you have an application that uses jQuery Mobile and you happen to have an XSS there, but there's a strict dynamic content security policy, this is how to bypass it. And finally, let's get back to the traditional content security policies. The ones without unsafe eval, without strict dynamic, without unsafe inline, which we kind of left out of this presentation because it's pretty obvious how to bypass them. It wasn't that easy to bypass those content security policies for two reasons. We couldn't use any gadgets that end in inner HTML or eval call because this would be detected by content security policy. And we couldn't add new script elements because there's no strict dynamic. We would had to know the correct nonce, for example, or the script element would have to be loaded from a trusted whitelist, which is obviously something we as an attacker do not want to. Fortunately, we were able to bypass such CSPs with gadgets in expression parsers. And as a bonus, it turned out that the very same vectors also work for all the other mitigations, so we won't complain. What do I mean by the expression parsers? So there's several JavaScript frameworks that have templating libraries or templating component inside of them, and they allow for certain, they have like a certain custom language for the expressions that could be embedded into the HTML. And those expressions, for example, this customer.name expression is meant for, I believe it's Aurelia code. It's meant, it instructs the Aurelia framework to insert a property name of some object called customer into this table cell element when rendering the website. This yellow code, the customer.name, is not JavaScript. This is some custom language created by the Aurelia framework in this example, that gets passed by Aurelia and then later on evaluated. So what Aurelia does is it creates a chain of functions that will eventually fetch the name property of some customer object and then insert it using inner HTML or inner text into this TD element. It turned out that with sufficiently complex expression languages in those frameworks, we can actually run arbitrary JavaScript bypassing CSP. As an example, there has been prior research bypassing the AngularJS sandbox mechanism by, for example, Maido Heydrich and then other researchers. And this is an example of actually gadgety behavior in AngularJS. But we kind of generalized that concept or built on this. So this is how you exploit the Aurelia into executing alert, essentially. Let's see what's happening. So first of all, we create a named reference to this div element. We name it simply foo, such that we can refer to it later on. Then you can observe that we try to bind to something. This means that we instruct Aurelia to pass the value of this attribute as this custom expression. So what we do is we get the reference to this div element, then we check the owner document property that happens to be the document object. Then from the document object, it's pretty easy to get the reference to the window, which is the default view. This is already a property of DOM. And then once we have a reference to the window, we simply call an alert function with parameter 1. This is, so we are able to convert the existing custom expression in Aurelia language into something that results in arbitrary JavaScript code execution by getting the reference to the window object. And this particular payload would bypass all the mitigations, so both web application firewalls, XSS filters, and all variants of content security policy. But there's more, right? There's a couple of frameworks. Each of them have different expression languages, and this is, for example, how you would do it in Polymer. We inject a template element with a couple of expressions. So first, you have to read it bottom to top for reasons. First of all, we overwrite the private root data host property, which is something akin to this object in JavaScript, with again a reference to the window. And then we are able to call the alert function bound to the window object that we overwrote just before. And actually the second argument is simply ignored. So this is again an alert through the expression language of Polymer. It turns out that we are able to bypass the content security policy in a couple of frameworks tested. So as for the whitelist-based CSP, we are able to find bypasses. We were able to find bypasses in 3 out of 16 frameworks. For nonsense, it's 4, and all the other variants are obviously more or easier to bypass because of them relaxing the content security policy and enabling some of the gadgets that wouldn't work in the base case. This is just a sample of the research that we did in the JavaScript libraries. We found, I think, over 50 gadgets, something like that. We were able to bypass. Our success ratio for bypasses was over 50%. And every tested mitigation was bypassed at least once. And there's a GitHub repository with all the examples. Also, this will be present on the Black Hat website, I believe. Almost all libraries turned out to have gadgets that are interesting, with the exception of React and Ember.js, because it only had a gadget in like a development version of or development deployment of the library. And it turned out that the gadgets in the expression parsers are the most powerful. So XSS in Aurelia, AngularJS, Polymer can bypass all the mitigations. So please don't have XSSs in those applications, or don't trust mitigations to stop them from being exploitable. And with that, I'll hand over to Sebastian.
Okay. Thank you very much, Koto. In the first part of this presentation, we saw gadgets and libraries. And we actually did this analysis manually. So it took a huge amount of time to investigate the source code of the libraries, to find these gadgets, to build exploits, and so on. But we also wanted to do something at scale. We wanted to see what is the status of gadgets in the web and in websites, or popular websites. And this is actually work that we've done in cooperation with Martin Johns and Samuel Gross from SAP. And I will show you what we found out. So what we were interested in is how common are gadgets in custom code. So just custom websites, code that lives outside of libraries. And we thought that gadgets, or the number of gadgets, might be different in that code, because libraries are very generic. So it might be pretty obvious that you have some gadgets there, but custom code is more specific, and maybe there are less gadgets, or maybe even more, we don't know, right? And also we thought about how can we address or fix this issue. If we have just gadgets in a few libraries, like 16 libraries we investigated, then we could probably go and just fix all these libraries, or try to remove the gadgets from them, or somehow put safeguards in place. But if gadgets are everywhere in all the websites, then it will be pretty hard to address this problem. So in order to do this research, we need to have some way to automate the process of finding gadgets. And that was quite non-trivial. So what we wanted to find is something like this. So here we just see a very simple gadget in userland code. So this uses jQuery. It reads a div element and extracts a data attribute from this element, and then just assigns it in HTML. So while this uses a library, this code is custom code, right? And in order to detect examples like this, we built a taint tracking engine. So taint tracking is the process of tracking user-controlled or tainted data throughout the execution and follow it until it reaches a security-sensitive function. So we built this into a Chrome and also a Firefox browser that enables us to track strings in the JavaScript engine. And here we have this very simple example where we just read a data coming from the DOM that we assume is user controlled, because we have an XSS and can inject elements into it, into the security sensitive property in HTML in this case. So what we do is we take websites and load this into our taint engine, and our taint engine will report these data flows. So after executing the function and executing all the JavaScript, we know, hey, there was actually a data flow from the DOM into this security sensitive function. Then we pass on this data into an exploit generator. The exploit generator will look at this data flow, try to come up with an XSS exploit, and create a piece of HTML that triggers the gadget in the page. So in this case, we know, hey, this was read from a div element. It had a certain ID and a certain class or whatever, and the attribute where the data was coming from was the data text attribute. So we can simply just create this element. And then subsequently, we simulate an XSS in the page and the test. So we just inject this back, and we injected this HTML snippet into 6 different positions to see when different gadgets trigger and how they can trigger. And then what we did is we ran this tool on the Alexa top 5,000 websites, and we built a crawling extension for our Chrome and Firefox browsers, and basically just crawled all the top 5,000 URLs and the first level links. So all the URLs that we found, and these links could either be located on the main domain or on any sub or super domain of this page. And in total, we found about 650,000 URLs that we crawled on about 4,500 domains. It's only 4,500 because in the Alexa top 5,000 websites, a lot of sites redirect. So for example, all the Google top level domains like google.de, google.fr and so on, they all redirect to google.com. So in the end, the data set is a bit smaller. And then we ran this exploit generation and injected all these gadgets into these pages, and actually we were able to verify about 285,000 gadgets in these 650,000 URLs. These gadgets are not necessarily unique, but we found them on 906 domains. So what we can say here, or what is the key takeaway of the slide, is that about 1 in 5 websites have a verified gadgets in userland code. However, this number is a very conservative number because our exploit generation and gadget verification was focused to be false positive free. And we got this false positive freeness by accepting a high number of false negatives. And actually we started looking into the data flows that we found manually, and we found that a lot of the things that we were not able to exploit automatically were also vulnerable and also had gadgets. And that's why we believe that the real number of gadgets in websites is much, much higher. But we are at least sure it's at least 20%. So based on this data, we started the security analysis and wanted to look at specific mitigations. And we all know that there is a lot of research on bypassing web application firewalls and XSS filters. So we wanted to focus on the other two mitigations, on HTML sanitizers and the content security policy. Let's start with HTML sanitizers. So basically the question that we asked ourselves is whether HTML sanitizers are secure in the default settings. And we saw that a lot of sanitizers regard certain HTML attributes as benign. For example, most sanitizers that we looked at allow ID or class attributes to be present in the sanitized string. Also, some sanitizers allow data attributes because they usually just contain data that is not security relevant, right? So what we found that out of the data flows that we found on these pages, 78% of all domains had a data flow from an HTML attribute into a security sensitive function. And furthermore, 60% of all the sites exhibited a data flow from a data attribute into a security sensitive function. So what this tells us is that it's probably not secure to allow data attributes by default in HTML sanitizers. And when you use HTML sanitizers, you should be very careful. So usually some sanitizers have settings where you can like configure that data attributes are not allowed, and for some sanitizers it's an opt-in approach, and some other sanitizers follow this opt-out approach. So be careful when using them. We also investigated the ID and class attributes, and we found that ID attributes or flows from ID attributes are present in 16% of all the sites, and flows from class attributes are present in 10% of all the sites. So ID and class attributes are not that, doesn't seem to be that security critical, but still there is a certain probability that you can bypass a sanitizer using those attributes if you find the right gadget. Okay, let's look at the content security policy. So here we asked ourselves how secure are different CSP keywords. Koto already introduced them, and here we just looked at the CSP unsafe eval keyword and the CSP strict dynamic keyword. And for unsafe eval, so unsafe eval is a weird weird keyword because until now it was considered to be safe to specify it in a policy. And if you actually look at real world policy, most policies will contain the unsafe eval keyword. Because usually the logic is, well, it just re-enables eval, which a lot of websites use. But the idea is you could just audit all the places where you use eval and make sure you don't pass user input to eval, and then you're safe. But that's actually not true for gadgets. And we found that 40% of all the websites had a data flow from a benign HTML piece, either a text inside an element or an attribute, into eval. So it seems that eval is considerably weaken the policy. The same holds true for strict dynamic. So for strict dynamic, we investigated all the data flows that go into script elements. So where we can either assign to an existing script the text, or where we can control the URL of an existing script tag, or where data is passed to the jQuery.html function, because that again takes the string, creates a script text from the string, and inserts that to the DOM. And we also checked whether we can create new elements where we control the tag name and at the same time control the tag of the tag name. And surprisingly, we found that 73% of all websites have these data flows, so that's pretty high. So what we conclude from this data is that strict dynamic and unsafe eval considerably weaken a CSP. And so you should be very careful when using this, and make sure that you don't have any gadgets on your page when you specify those keywords. Okay, let's come to the summary and conclusion. So in this presentation, we showed you how XSS mitigations work. They work by blocking attacks and not preventing XSS vulnerabilities. And they mainly do so by distinguishing benign HTML code from malicious HTML code or potentially malicious HTML code, and then block the malicious ones and allow the benign ones. Furthermore, we showed you that you can use gadgets to bypass these mitigations by injecting these benign HTML constructs that are then upgraded by an existing code in the page to code execution. We've also shown you that these gadgets are prevalent in most modern JavaScript libraries. So if you use JavaScript libraries in your websites, you're likely vulnerable to this attack. And we've also shown you that at least 20% of all the websites in custom code have these gadgets. But the real numbers are probably much higher in practice. So where do we go from here? So the main conclusion of this talk is that it's difficult to build secure applications. And just think about it. Hire a graduate student and tell him who has never been taught about security, who has not much experience, and just tell him to write a very complex web application. Do you think it will be secure? And I guess we all agree that it's probably very hard to get a secure application out of this, right? And the problem that we are facing is that the web hasn't changed in 20 years. So everything in the web is about turning strings into code. HTTP and HTML are based on taking a string from a server, turning it into the code. All the functions that we see in the DOM are based on turning strings into code. We have about 65 functions that take a string and that will result in code execution inside a browser. And we think that this gadget research shows that this is the main reason why XSS still exists, and all the approaches and all the things that we've done to try to prevent or mitigate XSSs actually focus on upper levels. We've never changed the platform. And we believe that for making the web secure and fighting XSS, we need to make the platform secure. So what we need to start working on is we need to get rid of all those string to code APIs in the browser. We need to have secure by default APIs, and we're actually going to work on this in the next few months. In parallel, we can also explore other primitives. For example, we see that isolation techniques are pretty effective at preventing or at least isolating or sandboxing XSS. For example, we already have the sub-origins proposal, or we have sandboxed iframes where you can basically separate certain parts of an application from each other, so that if you have an XSS in one part, it cannot spread to the other part or cannot be used to exploit other sensitive applications. There's also the isolated scripts proposal of Eduardo, and I think we should think more about how we can isolate or partition web applications in this way. Okay, with this I would like to thank you for your attention, and I think we still have time for questions, so feel free to ask them or just approach us after the talk. I think there's a question. Can you go to the mic and ask the question?
Are you guys going to open source your JavaScript taint analyzer?
Probably not. The problem is the infrastructure is very, very complex right now. And so we are thinking about open sourcing the taint engine, but it will probably take a long while to do so, and we're not sure if it's going to happen. So.
Stefanos, there is one that is open source, right?
Yes, there are a couple of opens. Yes, there is one on GitHub, I think, but it's difficult. It's just a patch set, so you need to patch it on your own into the Chrome browser and probably update the browser because it's old. So it's kind of difficult. More questions? Okay. There's a question. Can you go to the microphone? Oh, there is one.
Search any of the legacy versions of these frameworks to determine fragmentation issues, right?
Can you repeat?
The older versions of these libraries, is this all the newest stuff you guys reviewed, or did you guys go through maybe?
So we didn't look at the, let's say, like the backlog of the libraries. What we looked at was the current version of every of those libraries at when we did the research. It was a couple of months ago. So if that answers your question. We didn't have the resources to manually analyze all the history.
Yeah, I was just going to say the impact to custom and the deviation over your percentage of findings on true positive, I'm sure is a lot greater with people that are using outdated systems, right?
Yes,
so then
but
you're
that's
exponentially increasing
that's
that
like a
based on-
known thing.
So one more comment to this question. So we found a couple of interesting behaviors in different versions of libraries. For example, jQuery is an example. So in jQuery 1, jQuery will just eval all the script tags that are in user input. In jQuery 2, it has this branch, and when the script starts with use strict, so activates a strict mode, it will append a script, otherwise it will eval it. And in version 3, it actually just appends the script to the DOM. So sometimes, depending on the jQuery versions, you have different types of bypasses. So the jQuery version 1 bypasses, for example, CSP unsafe eval, while the jQuery version 2 bypasses unsafe eval and strict dynamic, and 3 just bypasses strict dynamic. So there's some kind of variation and some kind of interesting mixture. Sometimes you also see that libraries are using other libraries. So many libraries fall back to jQuery functionality. And so, for example, you sometimes see they check for the dollar function, and if the dollar function is there, they will use the jQuery function. Right. And that actually depends on the jQuery library version, which gadget you have in the page,
right.
Which is kind of an interesting behavior.
Okay.
So you can.
Great job.
Maybe the last question?
Yeah. So in your research, you said you were not able to carry out this bypass of XSS in React.js, right? So will you say that using React.js to build your UI, you will likely avoid XSS cross-site scripting issues?
Do you want to take it or? Yeah. React is special in the way it handles DOM interactions. So most templating systems work by you specify a template in HTML, and then the library picks up the template and renders it to the DOM. So there's this reading and writing. And React is different because it uses a compiler. And actually, in React, you specify the templates in your JavaScript file, and the compiler will turn this into JavaScript code. And the direction is always only writing to the DOM. So React never reads from the DOM, but always just refreshes things. And that's why we didn't find gadgets, because you can inject something, but if React doesn't read it from the DOM, it will not write it. So in that regard, React is better, and that's why React is not prone to gadgets.
Thank you.
Did you try using the taint analysis to find gadgets also in libraries?
I mean, our user-led code study also contains data flows that are in libraries, and but most of them are triggered outside of the libraries. So we looked a little bit into it, but it's hard to distinguish, right? We just collected data flows. Some of them come from libraries, some of them come from custom code. So the answer is yes, but we don't have like dedicated results for that specifically focus on libraries.
Okay. That's it. Maybe in the wrap-up room?
Yes. Yeah, if you have further questions, we're going into this room down the hall.